To start off our discussion of inverse functions, I want to first refer us to a problem. Sine inverse of -1/2 equals what angle? So we're talking about the inverse functions. We have that little -1. The inverse functions take in the sine value or the ratios and it spits out the angle. So it is the opposite of the original sine function. So what we're looking for is what angle has the sine value of -1/2. When we look at our unit circle, remember that the sine values are all of our y values. When we look at the unit circle, there's actually two places where the sine value is -1/2. And the angles that we might report would be 330 degrees or 210 degrees. Well, what I want you to do, I want you to take out your scientific calculator or whatever calculator that you have, and I want you to make sure that it's in degree mode. And I want you to type in sine inverse of -1/2. And then I want you to hit enter. What answer does your calculator give you? Well, your calculator will give you -30 degrees. So it completely skips this angle altogether, and it gives us 330 degrees, gives us that spot, but it thinks of it as a negative angle. So if you were to start here and then you were to go in the negative direction 30 degrees, it gives us this spot right here where the sine value is -1/2. So the question is why does your calculator not give you 330 or 210, and why does it give you a negative angle? Why does it think about this as a negative angle? That's the question we want to answer in this section of notes. So in order to answer that question, we need to first recall from algebra what is a function. So from college algebra, we talked about what a function is. And remember that for a function, if I put one x value in, I only get one y value out. So there's only one answer for every input. So when I put an x value in, we only get one y value out. And that's a function. Well, not every function has an inverse function. An inverse function, when we talk about inverse functions, we talk about switching around the x and y values. So if I have f inverse, that little -1, the output value becomes the input value, and the input value becomes the output value. So it reverses the ideas of the inputs and outputs. So inverse functions reverse the original functions. Well, in order for a function to have an inverse function, when I switch around the x's and the y values, we still have to have that property that for every input, I only have one output. We only get one answer out. So the idea is that the x and y values will switch places, and we want to compare this to a function that we should be somewhat familiar with, our square function. Just shrink this down a little bit here. So here's our square function, and this is actually the function x minus 3 squared. So we're going to take the square function and we shift it to the right 3 units. So we want to look at this picture here. Now, this is not what we would call a one-to-one function. Remember that if it doesn't pass the horizontal line test, we would not call this one-to-one. So this is not a one-to-one function. That means that if I were to take this picture and I was to reverse the ideas of x's and y's, then we would not get a function. So what we have here passes the vertical line test, and I could call it a function. So it passes that vertical line test, so this is a function. But when I look at its inverse, we run into a little bit of a problem. So first of all, the idea of an inverse is that we take the original points, so this would be 3, 0, and the inverse function reverses the order of those points. So instead of 3, 0, the inverse function would take in a 0 and spit out a 3. So it reverses the x and y values of the points themselves. And here we have 4, 1. So in the inverse function, that would become 1, 4. But it also has 2, 1. And on the inverse, that would become 1, 2. So we can keep going with this idea. This graph has the point 5, 4. So on the inverse, that would become 4, 5. But it also has the point 1, 4. So the inverse would be 4, 1. And let's do one more point. That would be 6, 9. So over here we have 9, 6. And 0, 9 would become 9, 0. So the inverse would look like this. Switching around the x and y values, this would be the inverse. The problem is, once I graph the inverse, it fails the vertical line test. That is not a function. So we want to make this have an inverse function. So not just an inverse, but we want the inverse itself to also be a function. So in order to make the inverse a function, I would need to get rid of about half this graph. So starting here, if I get rid of the bottom portion of the graph, then the top portion, so just from here up, would actually pass the vertical line test. So the top part would be a function. So in order for this to have an inverse function, I would have to get rid of a portion of the graph. So let's say we get rid of the left portion of the graph. Now, what we have here on this side would become the inverse function. So if I restrict the original domain, so I limit the x values that are allowed into the function, then when I reverse all of the x and y values, I get something that is also a function. We would call this the inverse function. Well, how do we restrict the domain? Well, when I look at the original parabola, that original square function, if I get rid of the left half of the graph and I only use x values from 3 to positive infinity, then I can actually find an inverse. So that would be the restricted domain. Notice that the range, of course, would be the y values that are used, and the y values start at 0 and then go up from there. So 0 to infinity would be the range. When I look at the inverse function, notice that the y values actually start at 3. So the domain goes from 3, and then the graph goes up from there, so to positive infinity. So the domain and ranges actually switch places because all of the x's for the original function become all of the y's for the inverse function. The whole idea of inverses is that domain and ranges, or x and y values, switch places. The range should become the domain of the inverse. So when I look at the domain, what are the x values? Well, the x values start at 0 and then go toward the right forever. So the y values of the original function become the x values of the inverse function. So the whole idea here is that in order for the original function to actually have what we would call an inverse function, that we have to restrict the original function so that it is 1 to 1. Once I get rid of that left-hand side, then the right-hand side is a one-to-one function. Therefore, the inverse will be an inverse function. So we want to examine the inverse sine function. So in order for the sine function to have an inverse, we would first consider the original sine function. So when I look at the original graph of sine, we notice that if I actually looked at the complete graph, that it would not be one-to-one. So the original sine graph is not one-to-one. It would not pass the horizontal line test. And in fact, it fails it many, many times. So it's definitely not a one-to-one function. So we want to make it one-to-one. I want to make it pass the horizontal line test. So in order to do that, we're going to restrict the original domain. I'm not going to use the entire graph. I'm only going to use the graph from negative pi over 2 to positive pi over 2. So we're going to restrict the domain to go from negative pi over 2 to positive pi over 2, which of course is the same thing as negative 90 degrees to positive 90 degrees. Well, what that also means is that we're considering these angles right here to be negative angles. So we start at 0 and we go in the negative direction to find those angles. And this is quadrant 4. And then quadrant 1 would be this portion here from 0 to positive pi over 2. So we restrict our original domain. Now when I switch around all of the x and y values, this is what we would call our inverse function. So the inverse function, that's sine inverse of x. We also use the word arcsine. Arcsine is the same thing as the inverse, so these words mean exactly the same thing. But when I flip the function, when I restrict my domain and then I switch all the x and y values, now that we see that the inverse is actually a function. Okay, but the output values, negative in, negative out, the output values are negative angles from quadrant 4. So the original function then, it has a restricted domain from negative pi over 2 to positive pi over 2, and the output values were sine values from negative 1 to 1. Well, now we're going to switch that around. Since we're talking about the inverse function now, the original domain, that restricted domain, will now become the range. These are the output values. And the original output values now become the input values. So the domain and ranges now switch places. So when I am choosing an angle, when we put something into the inverse function, any sine value, the angles that come out will come from quadrant 1, or they will come from quadrant 4. But you notice that the angles will be measured in negative values. So it's negative 30 degrees or negative pi over 6. All the way to negative 90 degrees or negative pi over 2. So if I was looking to find the exact value of y in each of these equations, so I'm going to scroll up just a little bit, make this a little bit smaller. There we go. If we were asked to find the arcsine value of square root of 3 over 2. So what we're actually looking for is an angle, and we have to pick from quadrant 1 or quadrant 4 since we're working with the inverse function. And we want to know what angle has a sine value of square root of 3 over 2. And that's a positive value. So when we look at our unit circle, I'm going to choose the point that has a y value of square root of 3 over 2, which would be here. And that's a positive value. And I'm only looking in quadrant 1 or quadrant 4. So the y values are positive in quadrant 1. So that angle would be pi over 3. So we could say that y is equal to pi over 3. So that would come from quadrant 1. For part B, when I'm looking for an angle, we have to look once again for an answer, an angle from quadrant 1 or quadrant 4. This time we're looking for an angle that has a sine value of negative 1/2. Well, when I look on my unit circle, a y value of minus 1/2 from quadrant 4 would be right here. Now the answer that we give has to be the negative angle. That would be negative pi over 6. So the inverse function would spit out negative pi over 6 as that input, as that angle. So if I put in a negative 1/2 sine, negative in, for that inverse function, we get a negative value out. And that's all because of the restricted domain and range, so that the function, the inverse function, could be 1-to-1. The inverse cosine function is very similar to the idea of the sine function, that inverse sine function. However, when we look at the cosine function, so we said that the function, the original function, would have to be 1-to-1. And if I consider the entire cosine function, we have a problem very quickly that is not 1-to-1. It does not pass that horizontal line test. So in order to force it to become 1-to-1, so that we have an inverse function, we're going to restrict the original domain. So we're going to only use the portion of the cosine graph from 0 to pi. So if I use only the portion of the graph from 0 to pi, we see that it passes the horizontal line test. It will be 1-to-1. Of course, that's the same thing as 0 degrees to 180 degrees, which means we're working with quadrant 1 and quadrant 2. So when we go to actually find the inverse function, we switch all of the x and y values, and we get what we call the graph of the inverse cosine function, which of course that would be cosine with a little -1, or y equals arc cosine of x. So arc cosine is the same thing as the inverse function. When we go over here and we switch all the x and y values around, we see that we actually do end up with a function. This definitely passes the vertical line test. So because of this restriction on the original function now is restricted to be from quadrant 1 and quadrant 2 from 0 to pi. And the original output, that should be cosine, not coine, but cosine. The original cosine values will come, the output values are from -1 to 1. Well, now for the inverse function, the original inputs now become the outputs. So the angles that get spit out, the angle solutions have to come from 0 to pi, so from quadrants 1 and quadrants 2. And the input values are now the cosine values. So the old range becomes the new input, or the new domain. So we're looking to find the exact value of y. Once again, we're looking for an angle, and we want to know the angle that has a cosine value of positive square root of 2 over 2. And we have to look for this angle in quadrants 1 and quadrants 2. So we're looking for a positive x value of square root of 2 over 2, and so that angle would be positive pi over 4. In example, or part B, we're looking for an angle. So we're looking for a y value of an angle that comes from quadrants 1 and quadrants 2. And we're looking for an angle that has a cosine value of -1/2. So that we're looking for an x value of -1/2. Well, that angle would be 2 pi over 3. So our angles only come, for the cosine function, our angle answers only come from quadrants 1 and quadrants 2, all because of that restricted domain and now the range for the inverse function from 0 to pi. For the inverse tangent function, when we look back to the original function is actually 1-to-1 if we look at only one period of the original tangent. So the original graph of tangent, that one little basic shape that we are very familiar with, goes from -pi over 2 to positive pi over 2. And so we don't have to do too much here. It's going to be that familiar portion of the graph where it is 1-to-1 from negative pi over 2 to positive pi over 2. And when we switch around all of the x and y values, then we actually get an inverse function. So this is passes that vertical line test that we need for a function. And the output values, the y values, come from quadrant 4 and from quadrant 1. And just like sine, since we go from 0 to minus pi over 2, just like sine, we're going to go from negative 90 degrees to positive 90 degrees. And because the endpoints are asymptotes, we won't actually get out an angle for the endpoints. But we think about quadrant 4 angles as being negative, because we go from 0 to negative pi over 2, from 0 to negative 90 degrees. All that's due to that restricted domain. So for the original function, we were restricting our original function to have a domain from minus pi over 2 to positive pi over 2, not including the asymptotes, those endpoints. So for the inverse function, that domain will become the range. So the angles that we choose from come from quadrants 1 and quadrants 4, where the angles in quadrant 4 are considered to be negative angles. So very similar to the idea of sine. So here we are looking for an angle, and we're talking about arctangent of 1, so we want to figure out an angle from quadrants 1 and quadrants 4, who have a tangent value of 1. So if we recall, we have a positive 1, so the answer has to come from quadrant 1. And to find tangent, we divide y divided by x. And any number divided by itself would be 1. So this would end up with a tangent value of 1. And that angle would be that pi over 4 family. So the y value that we're looking for, that angle that we're looking for, would be pi over 4. Now what if our angle is negative? Or what if our tangent value is negative? So now we're looking for an angle in quadrants 1 and quadrants 4. So one of those two quadrants that has a negative tangent value of negative pi over 3. So remember this, we're thinking about the y divided by the x. So in order to do y divided by x and get negative square root of 3 basically over 1, that would be our pi over 3 family, so that's negative pi over 3. So we think about that angle from quadrant 4 as being a negative angle. So the answer for that would be negative pi over 3. Here's a summary of the inverse functions and their domains and ranges. So sine inverse, the angles that we choose from, the output values for sine are going to come from quadrants 1 and quadrants 4. And remember that the angles in quadrants 4, we think of them as negative angles. Cosecant, the reciprocal function, has exactly the same range, meaning that we choose also from quadrants 1 and quadrants 4. And once again, the angles in quadrant 4 are thought of as negative angles. Tangent and cotangent. Tangent has output values that come from quadrants 1 and quadrants 4. However, I want to keep this in mind. For cotangent, the angles that we choose come from quadrants 1 and quadrants 2. So these are the only two that have a reciprocal relationship that are different output values for those inverse functions. Both cosine, the inverse function for cosine, and the inverse function for secant both come from quadrants 1 and 2. So we can actually use the reciprocal relationship to determine the angles for cosecant, cotangent, and secant. So let's look at a couple of examples of that. For example 4, we are looking for the exact measure in degrees of the indicated angle. So we are looking for arc cosecant of the cosecant value, -2 divided by the square root of 3. And so we're looking for the angle that has that cosecant value. To determine that cosecant value, we can use the reciprocal function to help us think through that. When the angle has a cosecant value of -2 divided by the square root of 3, then at the same time we are thinking about a sine value of the reciprocal. So we can use the reciprocal of both. So the reciprocal of the function, reciprocal of the input. So what we're looking for now is what angle has a sine value of -square root of 3 divided by 2. So the same angle that has a cosecant value of -2 divided by the square root of 3, that same angle has a sine value of -3 divided by the square root of 2. So what angle would that be? We look on our unit circle, and remember that we have to look for angles in quadrants 1 and quadrants 4. And we think about the angles in quadrants 4 as being negative angles. So this is our 60-degree family, so we'll think about that as -60 degrees. Okay, for part B, we're looking for the arc secant of -2 times the square root of 3 divided by 3. So we're looking for an angle, and the angle that we're looking for has to come from the same two quadrants that cosine comes from, which would be quadrants 1 and quadrant 2. And we're looking for an angle that has a secant value of that, but then also at the same time we can evaluate this by looking at the inverse function and the inverse of the input value, which would be, let's unrationalize that before we do this. Before we rationalize, the answer, or the value for the fraction would have been -2 divided by the square root of 3. So let's unrationalize and then we flip it. So that would be -3 divided by the square root of 2. And that's our 30-degree angle family. But we are supposed to find a value either in quadrants 1 and quadrants 2. In quadrants 1, the values are positive. So we're looking for an angle that has a cosine value that is negative square root of 3 over 2. So we are going to be looking in quadrant 2. And that's our 30-degree family. So that would be 150 degrees. So we look on our unit circle, find the x value on the unit circle, that's negative square root of 3 over 2. Find that cosine value, and that would be 150 degrees. So we're looking in quadrant 2 for cosine. Last one here, cotangent, inverse of -square root of 3 divided by 3. And for cotangent, we have to report values from quadrants 1 and quadrants 2. Just like secant and cosine, all three of those, we look in quadrants 1 and quadrants 2. And for this one, let's think about what the cotangent value is. Let's unrationalize first, so that would be -1 divided by the square root of 3. And remember that cotangent is x over y. So we look on our unit circle, we want to find an x value divided by a y value that would reduce to be -1 divided by the square root of 3. And of course that would have to be, before we simplify, that would look like this: negative 1/2 divided by square root of 3 over 2. We're looking in quadrant 2 because our value is negative. So what degree measure in quadrant 2 has an x value of negative 1/2 and a y value of square root of 3 divided by 2? And that would be our 60-degree family. So, but in quadrant 2, we're looking for 120 degrees. For example 5 and example 6, we will be using our calculators. And for the first example, example 5, we are looking for decimal degrees. So make sure that your calculator is in degree mode. So we're going to type this directly into our calculator. Arc, cosine, and this wouldn't be here. Just be arc cosine of this, and of course that's the same thing as cosine inverse of this value. So we're going to type that directly into our calculator. And we're going to round to the nearest 2 decimal places. So you should get negative, or 97.67 degrees. So theta has this angle theta has a cosine value that we were given here. And remember that cosine, our calculator is going to spit out values from quadrants 1 and quadrants 2. And this comes from quadrant 2. Theta equals cosecant inverse of this value. Now we don't have a cosecant inverse button on our calculators, so we're looking for the angle that has a cosecant value of this. Well, the same angle that has a cosecant value of 1.94, etc., has a sine value of the reciprocal. So we're going to look for sine inverse of the reciprocal of that value. So we're going to put that into our calculator, round to the nearest 2 decimal places, get 30.99 degrees. Now for example 6, we are looking for real number values. So we're looking for angles in radians. So we're looking for a real number, which is, in other words, for finding an angle in radians. And we're rounding to the nearest 6 decimal places this time. So we're going to directly compute this into our calculator. Sine inverse of this sine value. Remember that we're looking for an angle. And I get negative 0.133881. So there's the angle in radians that has a sine value of negative 0.133 and so on. Okay, the last one, we have y equals arc secant of this secant value. So we want to know what angle has this secant value. We do not have a excuse me. We do not have a arc secant button or secant inverse button in our calculator. So we're going to go to cosine. We're going to take the reciprocal of the function and then the reciprocal of the input. So we're going to put this under 1. We're going to take the reciprocal of the function and the reciprocal of the input. So we're looking for an angle that has this cosine value. We're going to type that into our calculator, and I get a radian value of 2.48024. So this is our angle in radians that has a cosine value of this value, this fraction, and a secant value of the reciprocal.